However, today I wanted to tell you about chaos. That's why we are here, to teach you how to deal with things where everything falls apart, nothing is stable, but they are governed by deterministic laws. And I'm doing this because it's necessary to do them. So back to Lorenz equations. What are important things about Lorenz equations? I beg you to ignore, when you look at Strogas, there is something called water wheel. Pretend it was never in that book. Long diversion of no interest in the long run, so don't waste your time on it. Okay, bye. Chaos! Sometimes when I'm very lucky, there are courses in which I'm able to explode something on the lecture podium, but we now have nothing on lecture podium, nothing to explode. But chaos is an explosion. So the basic thing that goes back to Newton, but there is no way to do anything about it, and then goes seriously to the end of 19th century, Maxwell and Boltzmann and Poincaré, is we have these amazing laws of nature. At those times, there were Newton's equations, and there were electrostatics, magnetism, and electromagnetism, and fluid dynamics. There was several laws of nature which were formulated, tested, amazing, beautiful. And you might ask yourself, I have the law. Since Newton, we indoctrinated and writing laws in terms of infinitesimal changes. So if I have a status system and time goes by 1 femtosecond, what happens to the state? And the intuition is everything will change slowly. There'll be no singularities explosion. They're very exceptional. We have to preserve energy mass. There's some, it should be the same in Tokyo and here. There are some ideas, and today and tomorrow. Symmetry deal. And out of that, plus some experimentation and observation, you write these amazing laws. And you look at them, and when they're done elegantly, they're very pretty. Gradient of F nu equals J, just few letters. And that's all of electromagnetism. Beautiful stuff. But you have no clue what these things do. It was very hard to figure out what the things do, because until the end of 19th century, people felt that they're supposed to write analytic solutions. And analytic solutions means is that you don't really know the answer, but you can give it a name, and then you feel you know the answer. So you say, the answer of my problem is mere G function of the second kind. Mere G function doesn't come in different kinds, but I'm just saying you give them names, and then you have some things that you can analyze by analysis, because that's all they had. Euler was a master calculator. Many of them could calculate, but what we calculate today has been delegated to machines, and they just couldn't do that. They had no clue about what are all possible solutions. The first serious attempt was made by Henri Poincaré, who developed qualitative way of thinking about what system described by law in terms of differential equations or partial differential equations for instantaneous changes. What do they look for long changes? One thing that soon very obvious, that you had to find equilibrium of the system, points in state space where nothing happens. And then you had to look at their neighborhoods, and that you could do by linear approximation until nonlinear terms kick in. Linear approximations can be very good. Linear equations have only two kinds of solutions. They're very simple. Either they have oscillatory solutions, sines or cosines, or they have exponential solutions. So both of them are exponentials, but they have either real or imaginary exponent. So the world of linear solutions is very small. And what they understood very early, that when they had oscillatory solutions, sines and cosines, they could do really good calculations. They could compute pendula and harmonic oscillators and Kepler ellipses, and then they could do some perturbative improvements to such calculations, do celestial mechanics. Everything was beautiful. But when you look at some random equilibrium given to you by God knows who, a man on the street hands you one, it's 50-50% chance that locally the thing is either oscillatory, meaning I push it and it just pushes back, so it oscillates, or 50% chance you push it and it's one of those other set of solutions of linear equations which are called exponentials. And the important exponentials locally are the ones that grow. So you push it, it goes away. If they're all contracting, you push it, no matter what you do, it just ends up in the hole. But the important things are these mixtures of stretching and so they're hyperbolic. Now, they had no clue to what to do with this stuff. In linear approximation, it just falls apart, explodes enough, you're done. It just runs away and nothing comes back. Not very interesting. In real world, systems which locally have the solutions are confined. They cannot burn infinite energy, they cannot go every place. So they're confined for some other physical reasons. So you leave locally and you come back globally. And that really was too hard to deal with until advent of computers. There are lots of conceptual ideas. Poincaré understood it, but he never drew a single picture in mécanique céleste, so nobody understood it. Certainly not physicists. Some mathematicians did understand it. And what is other solutions where everything falls apart, but it cannot run away because it's confined. So it's like a bunch of cats which are all running away from each other. But, they have to come and meet again because they cannot get away. Very few people were able to do this. And physicists from 1920 on, they just lost interest in this stuff, which was physics until 1920, because all the young people, the old people died, and all the young people learned only quantum mechanics. And that was a great thing because there was so much doing quantum mechanics. They did, both the miracles and errors of 20th century, and it still goes on, hasn't changed at all. It's incredibly powerful set of ideas. And only few thinking people who could afford to do this because they were not funded by funding agency, they were allowed to think in peace as professors in mathematics, thought about this problem. So there was a Soviet school who thought about, what happens when things fall apart, but they're not allowed to run away. In America, there was very little going on because it was, intellectually a third world country. Rockefeller Foundation was sending gifted natives from the United States, in this case, not real natives, but white immigrants to this continent. They were sending them to Europe to learn something. So a very few important Americans, like Oppenheimer, were sent to Copenhagen and Göttingen to learn the new stuff, which was quantum mechanics. And back in the backwaters, mathematicians were thinking, in particular, Gerrit Birkhoff was thinking what is called ergodic theory. So he was really formulating ideas about unstable systems. There are some simple examples which are motivated by statistical mechanics. There are billiards, bouncing balls, which obviously are chaotic because you hit them and they defocus in collisions. So things are all unstable, but they don't run away because they're on the table. So there was that kind of thinking going on. And they had graduate students. Now, in those days, there were few professors until roughly 50s or 60s, when, thanks to the atom bomb exploded during the Second World War, the number of physicists exploded and grew exponentially. But in those days, there were few professors and few graduate students, and graduate students had to do something else. That's also true today. So it's not often mentioned, but Birkhoff, the great person in the United States who thought about what we today call chaos, had a student, among many other ones, not particularly great among his students, called Edward Lorenz. Edward Lorenz got his PhD, and then he needed to get a job. And in those days, it was not, deep learning. The fad was, in those days, we need to know about weather. That was one of the obvious problems, that maybe people who knew how to compute, thanks to the advances of Second World War and first computers, maybe there'll be a better weather prediction, and that's immensely important. So Lorenz, with PhD in mathematics, became a weatherman, and he was not good enough for Harvard, so he got a job at MIT, which is what we call Georgia Tech of the North. It was one of those technological institutions. He was a very lucky man, because around 60-something, there were lots of ideas how we are supposed to think of weather, because the weather was supposed to be a fluid. There is air, humidity, clouds, atmosphere. There's a planet, which in those days was a flat planet, flat Earth. So there was a surface. There was sun, which was heating up the surface. And this fluid, the air, was heated from the bottom, cooled at a higher latitude by emitting radiation. So there was a flow of heat through it. And if sun was strong enough, it would set air in motion, and that's called convection, convective motion. If you take a good fluid dynamics course, you'll be taught the equations for that. But they're equations for the fluid, so they're infinite dimensional. They're formulated in a way that they're same in Sangen and Alabama. So they're spatially invariant, and they're in the same books for many years. So they're time invariant. They've been in the same books since 1820. So they're very time invariant. And the idea is, whenever you have translational invariance, there is a natural basis to diagonalize things which are translation invariant, and diagonalize derivatives and operators. That's called Fourier modes, Fourier analysis. Symmetries of our problems often force us to use those things. And in Fourier analysis, you trade in equations that describe what every virtual little microparticle in the fluid is doing, so infinitely many points with their velocity fields. When you run them through Fourier analysis and other orthogonal polynomials, not necessarily just Fourier basis, you get a discrete set of equations, ordinary differential equations, infinitely many of them, but they order themselves in a very natural way. They say the most important ones are the ones that describe small variations over the large system. They're called, long wavelength Fourier modes. And then the higher ones get kinkier and kinkier, but dissipation or loss to heat of fluid rubbing against itself, self-friction or viscosity as it called, kills off high Fourier modes. So it's possible to argue, and it's very well established in practice and computational practice, that you can replace infinitely many degrees of freedom of original formulation to a hierarchy of coefficients of Fourier modes, which you can truncate, meaning you can make it finite. Now, for honest work, we know today that we need of order of at least 50,000 to 1 million coupled ordinary differential equations to simulate, any interesting turbulent kind of weather in most ideal conditions. In early 1960s, this was, unimaginable dream. Other weathermen preceding Lorenz, but in same community, has whittled down this convective heating on a flat plane Earth to very few Fourier modes. So they brought it down by various physical and qualitative arguments to 13 coupled modes. So that was number one. These equations existed. Lorenz was one of the people who knew them. There's always a woman behind it all, and she's never cited. In 1945, Dame Cartwright, she was knighted by the Queen. Dame Cartwright, who was a part of the British war effort, she was studying vacuum tubes, what else, because radars are very important, and she discovered chaos. She was the first one to see a strange attractor, which will be a big thing in what we want to do. But, when you read this paper, it doesn't grab you. She was not in position to actually plot much of the strange attractor. And what worked in Lorenz's favor was that as a weatherman, he was funded. Being at Georgia Tech of the North, he was funded rather well. And they were throwing computers at people like that because it was first time where, kind of desktop or room full computers became accessible to people other than those that were making bombs. So Lorenz had access to a computer, and that meant that he could program that thing and that there would be an output, and the output would be a bunch of numbers, because that's what computations gave in those days. What he did is he said, I have these equations, I have this computer. I will put those equations on the computer and see how the weather develops, and whether these equations are in any sense a good description of evolution of the weather. That he did, and now we know the truth, is the help of two other women who actually did the programming. And it's only my friend Dan Rothman, who runs the Lorenz Center at MIT now, who bothered to go through the archives and discover actually calculations are not done by Lorenz. They were done by two other people whose name I forget. He ran this 13, and he looked at the numbers that came out, and he realized that for him, interesting regime, most of these 13 variables didn't do anything. They were kind of just went someplace and hanged around, not varying very much. And there were only 3 of them that were moving in the simulation. So he extracted them, he wrote them down, and I do not want to spend time pretending that these equations describe physics or weather. That's not why they're important. And please ignore the chapter or section in Strogat's called water wheel. Just look at Lorenz equations. So they had some logical reason. And the thing about nonlinear systems is that anybody who does something nonlinear will write some kind of equations like this, and they'll have always the same property, that you will look at them and you'll have no idea what they do. These are equations for 3 Fourier coefficients that have survived pruning from infinity, from first infinity to 13, and then 3 survivors. And there are 3 parameters here in purple, which person like Lorenz had some intuition what their value should be. And then the first equation is a linear equation, so that kind of equation we know how to solve. Second equation starts out okay, but then it has a nonlinear tail because x and z affect how this second component in state space develops. And The third one had a nice linear part. This is the simplest linear equation, extremely well. Its solution is exponential, function whose derivative is proportional to the function. But it had a nonlinear term that depended on two other variables. So there were three coupled equations, and nobody then and nobody now, given this equation, has any clue what to do with them. He got started. Now, what I will do now, I apologize, this is exciting, but what I need to do before we really appreciate the excitement, I need to finish what we started last time, and I need to finish telling you about how we think about stability and instability of solutions of then laws, dynamical equations. In this case, differential, but I already told you if you use Poincaré maps, there could be iterations in time. So laws can come in different shapes. Now, deterministic laws have a property that every initial condition has unique solution. So all the possible solutions, they organize themselves on lines in state space, which are called trajectories. So I will go back and discuss stability for a bit. And because, every time you learn a new thing, it's a bit confusing. One thing that's very confusing about how people tend to write these equations, X, Y, and Z remind you of Descartes and Euclidean coordinates. Here in 3 dimensions, there's coordinate X and coordinate Y and coordinate Z. These things are abstract and they have nothing to do with coordinates X, Y, and Z, our Euclidean 3-dimensional world. These are things that I would call fields. So when you started with the example of fluid moving, it meant that you had some volume and fluid was moving on this volume. The way you think about it is that you have some state and you need, for fluid, infinitely many numbers. And if you put it on computer, 1 million numbers to tell you what the state is. And that's a complete specification of instantaneous state of a fluid. Now, what's going to happen next? That's what equations of motions are for. So at every point in the fluid, there's a little arrow, which Strogatz call F, and I call V for velocity, but it's an abstract arrow. And your equation says, your first order differential equation says that in small step in time, you'll move in that direction by small distance proportional to the length of that vector. So that's a field. You think of it, there's a hillside and the grass is growing in it, the little blades, and that's why Germans gave it the name Feld, meaning field. They visualize it like that. But this is an abstract notion because your hill might be in 3 dimensions, but in physics, chemistry, etc., these states are described in thousands dimensions, million dimensions. In particular, when you go to these Fourier spaces, there are zillion dimensions that describe the field. Now the coefficient of a Fourier component is called the field associated with that direction in your basis set. So these are fields. These are not coordinates X, Y, and Z. What we want to know about these fields is when we integrate them, we learn how to integrate them. We are very good in integrating at least low dimensional ones for short times. We want to know, how good is our integration, which means if we have an uncertainty in specifying our state and uncertainty in specifying our equations, and then error due to approximate integration method like Runge-Kutta 5th order or whatever you like to use. We need to know how good this is, and that's called stability. That just says, how close or far away are the neighbors to my idealized state of the system, and where do they land with time? So that's stability in time. And I want to emphasize what I did in last lecture one more time. All of you know that there is a difference between x and e to the x. There is a difference between a number and exponential of the number. If you take the logarithm, then there is difference between logarithm of the number and the number. The big confusion in this kind of textbooks like Strogatz is that it's first easier to study equilibria of differential equations. The easiest possible thing is to say I have something that's not moving. Velocity field in instantaneous differential equation is not moving, and I want to know what its neighborhood does. So the idea is that, if I have some equations, like x dot is v dot, and the law doesn't change from today to tomorrow, I don't have variable rates or whatever, a force outside that's called autonomous system, this is like celestial mechanics, then the neighbor, my point, this is neighboring point, the distance to the neighbor, which is d-dimensional vector in maybe 100,000 dimensions or 3 dimensions, can be estimated by looking at the deterministic equation, expanding it to the first order. So for zero term is just the regional velocity, and the first order is a bunch of derivatives called velocity gradients. And there are other terms, but in linear approximation, we drop them.